record. Okay, so just from the beginning again, this is in your textbook. It's on page 229. You can go and read through it quickly, and then I'll just explain it. So if you look at the first diagram over here, the top one, everything is stationary. Stationary just means nothing is moving. So the source of the waves aren't moving and the people aren't moving. So there's no relative motion between the source and the observer. Cool. So that's what's happening in the first diagram. Then in the second diagram, if you zoom in a little bit, you'll notice that the source of the sound waves, or the source of the waves, are moving towards the left. And what this means is that on the left-hand side, relative to the source, the waves are decreased. And then if you remember that V is equal to, I can't do lambda on my keyboard, so I'm just going to say wavelength times frequency. You know that if the wavelength decreases, it means the frequency must increase. So therefore, increase frequency. Cool. So when the wavelength decreases, because of the equation, frequency is decreased. But what's important to remember is that the speed of the wave hasn't changed. It's still a sound wave, or it's still a light wave. And whatever the speed of the wave was in that particular medium, the speed of the wave hasn't changed. So I'll write that there. Speed of wave has not. What's changed is the wavelength. And because the wavelength has changed, you've also changed the frequency. Cool. So that explains the one on the left-hand side. And then you can do exactly the same on the right-hand side. So you can focus over here. If you focus on this side of the wave, hang on, sorry, I want to do that in a different color. If you focus on this side over here, you'll see that the wavelengths are slightly stretched out. So in this case, you would just say the opposite, and you would say here that wavelength length increases, and therefore so the interesting thing is that person A and person B will actually hear a different frequency of sound. The person at A will hear a higher frequency sound, and the person person B, the person on the right, will hear a lower frequency sound. Cool. Does that make sense? Everyone happy with that so far?
I'm so sorry, I had a Wi-Fi problem.
No problem, no problem. It's being recorded, so you can go watch on YouTube later. Cool. But the idea is that the observed frequency, or the frequency that the person hears, is going to be different to the actual frequency of the wave. Cool. So in the top picture, let's highlight that in green. Let's go back to the top picture, put you in green. In the top picture, everybody hears the same frequency. So if we go back to here, these two people here will hear exactly the same frequency. And the frequency they will hear is the frequency that's emitted by the source. Cool. So one very, very good example of this is when you hear an ambulance approaching. So I'll go to the iPad quickly and I'll show you. New share iPad. Well, just give me a second, the iPad's loading. Cool, so here's the page number and the equation that we're going to use. But let's say you're here, let's say you're in your house. Cool, so you're sitting over there, and the ambulance is coming towards you, and it's got that little siren at the top there. And that siren is emitting a sound at some sort of frequency. So let's just say that the frequency is 400 hertz. Cool. Then what you're going to say is that that ambulance is traveling at some sort of velocity. So it has a speed. And when I say speed, I don't mean the speed of the wave. I mean the speed of the actual ambulance. So let's say it's traveling at 30 meters per second. Cool. So when you're here and you're listening to the sound, this is you, will hear f greater than 400 hertz. So you're not going to hear 400 hertz. You're going to hear a frequency slightly higher than 400 hertz. So you'll hear a high-pitched noise relative to the thing. Cool. Then as it approaches, it's gonna come towards the house. So we can do this. Let's copy and paste. Copy, and then just paste it on a new page here. Paste. There we go. Now we're going to move that. We're going to move that object. So we're going to take it and we're going to go here, and it's going to be here now. Now it's going away from you. Cool. And when it's going away from you, you're not going to hear frequency greater than 400. You're going to hear frequency less than 400. Because now the wavelengths are stretched out. Because the wavelengths are stretched out, the wavelength has increased. So the wavelength has increased, and the frequency that you're going to observe is going to decrease. So that's why when you watch the video with the Doppler effect, it makes that sort of sound where it starts off as a very high-pitched sound, and then it goes to a very low-pitched sound. So high frequency and then low frequency. Cool. Everyone happy so far?
Yes.
Yep. Good. So it's quite a straightforward topic. Now what's going to make it tricky is that in the equation, if you look at the equation here, there is a plus and, oh, whoopsie, sorry, that's the wrong one. I need to use highlighter. If you look at the equation here, there's a plus and a minus. And I can't, honestly, for the life of me, I don't remember this, but the plus and the minus is used for when it's coming towards you or when it's going away from you. So honestly, for the life of me, I can never remember which one's which. So I have to always check the textbook. So if you look at the textbook on the next page, it tells you here somewhere where the plus sign applies to a receding source. So I'm going to highlight this here for you quickly. So a plus sign is a receding source, and receding means going away. So when the ambulance is going away from you, you're going to use a plus sign in the equation. When it's coming towards you, you're going to use the negative sign. So let me just go back to the iPad and then I'll share that. But it is in the textbook. You must just read it. It's all there. But that's the only thing that makes this equation a little bit confusing. It's when to use the positive and the negative. So positive here is going to be for away, and negative is going to be toward. Now, whether you use positive or negative, let's say you forget which one is which, the outcome or the observed frequency, whether it's higher or lower, will tell you whether you use the right one or the wrong one. So if you get an answer that's higher than the original frequency, it means that it's coming towards you. And if you accidentally use the wrong one, you would get an answer that's slightly smaller. Everyone happy so far? In other words, this equation gives you two different answers depending on whether it goes towards or away. So that we can have a look at it, do a worked example quickly. Let's have a look. Let's keep all of that. Copy, and then let's do a worked example. So here's our ambulance example. Here's the ambulance example. So we just have to make a couple of estimates. We have to say, let's say that the frequency of the source of the ambulance is 400 hertz. So that's the frequency of the sound emitted. V in this case is the speed of the wave. So it's the speed of the sound wave itself. And this is approximately 330 meters per second in dry air. Cool. And then Vs is the velocity of the source. So let's say that it's traveling at what's 10 meters per second. Let's say 30 meters per second is probably about 120 k's an hour. Cool. So that's the speed of the ambulance itself. Cool. Then the question is, what two frequencies will you hear in terms of the reduced frequency and the increased frequency? So I'll let you do that quickly. Take about 3-4 minutes. And I want you to tell me what are the two observed frequencies? What's the slightly higher frequency and what's the slightly lower frequency that you'll observe? Also write that down quickly and do that. I'm going to pause the video just so that we don't record dead time. Cool, so if you just use the equation, when it's going away from you, you're going to get 367. And when it's going towards you, you're going to get 440. And it makes sense because when it's going away from you, you're going to hear a lower frequency. And when it's coming towards you, you're going to hear a higher frequency. But do you notice that the change is not exactly the same? Do you notice that based on the 400, the increase in the one direction is not the same as the decrease in the other direction? Do you see that? So if you took 400 minus 367, you would get 33. So the change over here, and this is very important because this is how they sometimes like to ask the questions. Here, the change is 400 minus 367, which is equal to 33 hertz. And over here, the change is 440 minus 400 is equal to 40 hertz. So you've got to be very careful. This word change, the change in frequency is not part of the equation. The change in frequency is something you have to do as an additional calculation. You can't just plug in everything into the top equation and get the change out. You have to get the change from that. And then the other thing is, this is very important, you can't cheat and just do it once and expect the change to be the same for both directions, because you can see here that the change is not the same. So if it asks for both changes, you have to unfortunately do the question twice. You can't just do the positive and say, okay, well, because of the positive one was an increase by 40, then the negative one will be a decrease by 40. It's not a linear scale. It doesn't scale linearly like that. Cool. So that's something you've just got to be careful of when they ask for the change. Then I'll just show you quickly. So if you go and have a look at the questions, Doppler effect, you'll see that it's always observer and source. They talk about ambulances. This question here, I don't know what this is referring to. I'm not sure if it's a Doppler affected question or not. Just have a look at this question. See what you can figure out. I don't know what that is. But here we go. Here's one where there's a towards and an away, and then there's two different frequencies for each one. So you probably have to do the equation twice. Ooh, and it just so happens that it was traveling at the same speed that we had. Ooh, but I want to find one quickly that talks about a change. Here's one where you have to calculate the velocity of the train. In other words, you have to solve for v. So you put everything into the equation and solve for v. So it's not as straightforward as that. And then they give it to you in terms of a fraction. They tell you that the observed frequency is a fraction of the original frequency. So you've just got to think about how you're going to use that in the equation when you play around with it. Also, they don't give you the observed frequency. They tell you that it's a fraction of the original frequency. Then there's this one. Frequency heard at X, frequency heard at Y. This is just increase, decrease. You've just got to use qualitative analysis. There is one somewhere that talks about a change. I can't see it. Here we go. What is the change in frequency? There we go. Cool. So when they say change in frequency, you have to do the whole calculation and then subtract the original from the new one from the original, whichever one's bigger in that sense. Cool. So I'd say they're pretty straightforward, nothing too difficult. You've just got to play around with it. And just remember, it's exactly the same equation every time. You're not using any different equations. Cool. Any questions? Oh, you're good. Good. And then obviously just make sure that you go to your textbook. Make sure that you read starting on page 229. It's quite an interesting topic. I could tell you the explanations and I can tell you the relevance of it, but they talk about things like shifting galaxies and expanding the universe. And it is quite an interesting topic if you want to go and do a bit more research on it. But you can read in the textbook and then ask questions later if you want. Cool. I'll see you guys in chemistry. Chemistry, guys, take a break. I'll see you at 9:30. So you've got about 13 minutes, give or take. Ooh, go get something warm to drink. Hello.
Sorry, will we discuss the Doppler effect questions tomorrow?
We can if
Or
there's
will
no
we do new
questions.
work?
We'll discuss them quickly if there's questions. Yeah,
Okay.
but I don't think you'll have any problems with them. I think if you sit down and do them, if you do them properly, you won't have any problems. You should get all the correct answers, I think.
Okay.
Cool. So try your best, do as many as
Are
you
the questions
can.
already on Google Classroom?
They are. I put them up just before the lesson. I put them up at about 7:30.
Okay.
Cool. So I'll see you guys in about 15 minutes, give or take. So at about 9:30. Cool. See you guys.